Hello, I'm Matthew Lewis. I'm the Chief Technology Officer at Michigan Aerospace Corporation.
Hello, I'm Josh Cohen. I'm the lead ecologist with Michigan Natural Features Inventory, Michigan's Natural Heritage Program. We'd like to thank the conference organizers for including us in this event. While we are unable to be in Athens in person due to organizational travel restrictions here in Michigan, we're excited to share the results of our first year of research utilizing low-cost drones, high-resolution visible spectrum imagery, and deep learning algorithms to monitor for invasive plant species. Through work on this project, we have developed a novel but scientifically credible and affordable method for rapidly and precisely monitoring invasive plant species within rare and Great Lakes endemic coastal ecosystems. We're grateful to the Michigan's Coastal Zone Management Program and the National Oceanic and Atmospheric Administration for funding this project that fostered the unique partnership between Michigan Natural Features Inventory and Michigan Aerospace Corporation, bringing together scientists with expertise in ecology, biodiversity conservation, computer programming, remote sensing, and deep learning. In a nutshell, our monitoring protocol comprises a commercially available and easy to operate unmanned aerial system capable of collecting high-resolution imagery in a precise and repeatable manner, software enabling ecologists to annotate this high-resolution imagery to identify targeted invasive plant species, neural network-based algorithms for identifying species in images, and software for generating georeferenced heat maps of invasive plant species locations within rare coastal ecosystems. These site-specific georeferenced maps quantify invasive plant species density and distribution and provide resource managers with actionable insight to gauge risk to the site, plan biodiversity restoration, and evaluate the efficacy of control efforts. In this presentation, we'll provide an introduction outlining the need for rapid monitoring in coastal ecosystems, a brief overview of the focal ecosystems and targeted invasives, a discussion of our methods using uncrewed aircraft systems, or UAS, and deep learning algorithms, and we'll share our results focusing on density maps. We'll conclude with a brief discussion of lessons learned and recommendations for moving our platform forward. Michigan supports a wide array of coastal natural communities that are globally rare and endemic to the Great Lakes region. These ecosystems provide critical habitat for native biodiversity and an array of ecosystem services. However, they're increasingly threatened by invasive species. Invasive infestations are projected to increase as the landscape continues to be fragmented and the climate changes, and coastal ecosystems have been identified as vulnerable to both fragmentation and climate change. Depicted here is a Lake Plain prairie, a critically imperiled system being infested by glossy buckthorn and invasive reed. The study site that we focused on for our paper is Lake Plain Prairie, a critically imperiled ecosystem endemic to the Great Lakes that occurs in the southeastern portion of Michigan and is shrinking at an alarming rate due to the infestation of invasive species, including Frangula ulmus and Phragmites australis, subspecies australis, both pictured here invading Lake Plain Prairie remnant. Invasive plants displace critical habitat for native species, interrupt food webs, alter soils, hydrology, and disturbance regimes, compromise pollinator services, change microclimates, despoil recreational resources, and degrade the economy of the Great Lakes states. The rapid spread of a diverse array of invasive species across landscapes demands monitoring protocols that can match the pace and scale of invasive infestations and also be flexible enough to detect change in populations of a range of invasive species in different ecosystems.
The use of remote sensing to survey and monitor invasive plant species is a new but rapidly growing field. Most current studies aimed at mapping invasive plant species remotely use differentiation of spectral signatures of hyperspectral imagery. These techniques, however, are often coarse in spatial resolution, technically difficult, and too expensive to be practical for nature conservation and land management. New technologies will be useful only if they are fiscally and logically accessible to the relevant stakeholders, and if their application allows for questions to be answered at appropriate scales. Our goal was to develop a low-cost, inclusive platform accessible to a wide array of end users in the resource management field. We believe that the use of UAS in combination with machine learning is the best means of achieving this goal.
We'll now provide a brief overview of the study sites, focal species, field survey techniques, aerial campaign, and data processing methods. We selected a range of sites across the coastal zone of Michigan to capture regional variability of ecosystems and invasive species and test the rigor of our methodology. These sites were all identified by biodiversity conservation prioritization efforts and are endemic to the Great Lakes region. For the purposes of this talk and our paper, we will focus on Lake Plain Prairie, a globally imperiled ecosystem located in the southeastern part of our state. The ecological integrity of Lake Plain Prairie is threatened by numerous invasive species, with reed and glossy buckthorn being most deleterious. Glossy buckthorn is native to Eurasia and was introduced to North America as an ornamental. It impacts natural ecosystems by outcompeting native vegetation, decreasing light availability and soil moisture, lowering the water table, increasing decomposition rates, reducing the complexity of soil structure, and altering pollinator diversity and abundance. Invasive reed is native to Eurasia as well. It forms monodominant stands that outcompete native vegetation by shading and by forming a dense litter mat. Great Lakes coastal wetlands infested with invasive reed are characterized by reduced plant species diversity, reduced habitat for wildlife, waterfowl, and fish, reduced wetland functionality, and reduced recreational value. Each monitoring site was visited by a professional ecologist prior to the deployment of the UAS. Locations of target invasive plants and additional plants of interest were marked with high-precision handheld GPS. In addition, we used color-coded flagging to mark a sampling of invasive plant species within each site. Both the GPS waypoints and color-coded flagging were used to facilitate later identification of invasive species on high-resolution imagery. The ground campaign also helps us to determine where to focus UAS monitoring.
All unmanned aerial system flights for this project were compliant with Federal Aviation Administration guidelines and requirements, and all flights were conducted by a licensed UAS pilot per FAA Part 107 guidelines. We employed a DJI Mavic Pro mounted with a high-resolution visible spectrum camera with approximately 12 megapixel resolution. This UAS is inexpensive and can be carried in a backpack to reach remote areas. We used a commercially available drone deploy application to plan and execute monitoring and capture the high-resolution aerial imagery. Drone deploy allows users to define the monitoring area and set the flight altitude. With this input, drone deploy plans flight transects, allowing for precise, repeated monitoring. This image depicts the invasion of invasive reed, the blue flagging, as well as glossy buckthorn, the orange flagging, in a Lake Plain Prairie in St. John's Marsh State Wildlife Area. UAS flights were conducted during the lake growing season in 2018, when the targeted invasive species had reached their maximum growth and foliage has peaked. Flights were conducted in July and August at an altitude of 20 meters. A restoration crew cut and herbicided glossy buckthorn in July within a portion of St. John's Marsh. This allowed us to acquire pre- and post-treatment data.
Following our ground and aerial campaigns, we then launched into the most exciting desktop campaign. We designed and implemented cloud-based software to map and annotate collected imagery and classify species using deep neural networks. During the annotation process, ecologists inspected the aerial imagery and tagged pixels containing targeted invasive plants. Ecologists had access to all the collected ground truth data, both in the form of GPS waypoints, which were displayed on the georeferenced aerial images, as well as the color-coded flagging visible in the image itself. Over 2,000 distinct images were annotated, and over 97,000 tiles were labeled. Since this represents a fraction of the available imagery, the annotated tiles were further augmented by rotating, shifting, and scaling each annotated tile to produce many millions of additional training examples that were also fed into the convolutional neural network. Through this annotation process, we developed a library of digital images of the targeted invasive plants. Each annotation is associated with a small part of the image, a tile. These tiles are tensor objects that are 128 pixels by 128 pixels by 3 color channels. The collection of tiles and corresponding labels of the species of interest form the training data for the next stage of the process, the classification of species through machine learning.
To automatically identify invasive plant species in the aerial imagery, we used an approach known as deep learning, and more specifically, we used a particular neural architecture known as a convolutional neural network. You can think of a neural network as a fancy function that takes in some sort of input, a vector, an image, a time series, and it produces an output, a classification label, a real value, an action to take. This image shows the architecture of a convolutional neural network. A convolutional neural network contains specialized convolutional and pooling layers inspired by the mammalian visual cortex. Given training examples, CNNs can learn to identify objects in an image at levels exceeding human capability. We trained the neural network using the annotated image tiles with the species of interest labels produced via the annotation system previously described. The neural networks are trained by providing labeled images as inputs and providing desired classifications as the output. Here we depict how we parse and annotate the image data. When training neural networks, the annotated images for the target species and the confuser species are split into test, train, and validation sets. Neural networks are trained using the training set. Training progress is evaluated using the validation set. The overall classifier performance is established using the test data. Evaluation on only the test data ensures that we are not overfitting the convolutional neural networks to a subset of the data. The goal is to teach the networks to associate the input image with the correct output label. Once trained, the neural networks can be used to produce a variety of data products and performance metrics, including density maps, receiver operating characteristic curves, area under the curve values, and confusion matrices. We generated georeference density maps for glossy buckthorn and reed for the 2 Lake Plain prairie sites. These heat maps depict the density of the target species occurring within a site. Within these maps, the intensity of color is proportional to the probability of occurrence, with hotter colors depicting higher probability. This map shows the density of glossy buckthorn within St. John's Marsh State Wildlife Area. A restoration crew cut and herbicided glossy buckthorn within the Lake Plain Prairie at St. John's Marsh in late July 2018. A visual comparison of UAS collected high-resolution imagery from the treated portion of the site pre-treatment is shown in the above left, and post-treatment in the above right. These images reveal that a significant amount of glossy buckthorn was removed by the control effort. Using the density maps from pre-treatment, which is shown on the bottom left, and post-treatment, which is shown on the bottom right, we can quantify the impact of the stewardship activity. The control effort resulted in an estimated 85% reduction in glossy buckthorn within the treated area. These maps demonstrate the utility of this automated monitoring platform to help quantitatively assess the impact of treatment and plan for future control efforts. To evaluate the performance of our classifiers, we use receiver operating characteristic, or ROC curves. ROC curves provide us with a way to visualize the sensitivity and specificity of a classifier. That is, how well does it correctly identify the species of interest while not confusing it with other confusers. These curves plot the true positive rate of the classifier against its false positive rate, parameterized by the classification threshold. That is, the minimum probability required for us to declare an image to be belonging to the species of interest. In an ideal classifier, all images with probabilities above 0% would be correctly declared to be the species of interest. The classifier would never report a non-zero probability for a species that was not the species of interest. An ideal classifier then has a ROC curve that looks like a step function. The area under the curve, or AUC, is 1. A perfect classifier has an AUC of 1. The worst possible classifier has an AUC of 0.5, indicating that it does no better than random chance. Classifier performance is usually somewhere in between. Classifier performance was high. Glossy buckthorn had an area under the curve value of 99.4%, and reed had an area under the curve value of 96.5%. These ROC curves tell us that the classifiers have both high sensitivity and high specificity for a wide range of threshold values. Another way to visualize classifier performance is via a confusion matrix. In a confusion matrix, each row represents the average classifier predictions for an actual target against the classifier associated with the column library target. An ideal classifier would be diagonal, with a classifier probability of 100% only when a species matches itself, and 0 elsewhere. To the extent that there is any energy off the diagonal, it represents classifier confusion. That is, a classifier is confusing one species with another. For our dataset, the most significant confusion was between native and invasive Phragmites. This is to be expected as they appear visually very similar.
In our discussion, we will touch upon some of the most salient lessons learned and discuss next steps for improving our automated monitoring platform. Our platform represents a novel method for using UAS and machine learning to efficiently and accurately monitor invasive plants within a rare and Great Lakes endemic coastal ecosystem. We utilize UAS to collect high-resolution imagery. We developed software to facilitate the annotation of this imagery. We constructed convolutional neural networks to identify targeted invasive plants in the images. We generated georeference density maps of invasive plant distributions. And we successfully classified infestations of glossy buckthorn and reed in Lake Plain Prairie. The resulting maps of invasive plant locations provide resource managers with increased capacity to assess risk, plan interventions, and monitor the effectiveness of restoration efforts. With continued annotation and addition of species into digital libraries, we're confident that our convolutional neural networks will increase in performance as species-level classifiers. Our preliminary results from a year of study show the promise of employing UAS and deep learning algorithms to monitor invasive plant species impacts, focus restoration, and evaluate control efforts within open canopied ecosystems. To test the robustness of our methodology, we recommend evaluating these species across a greater range of sites and ecosystems to capture regional variability of these invasive species, as well as the ecosystems they are invading. In addition, we propose evaluating additional invasive plant species that are less distinct from their biotic and abiotic surroundings. To increase the accuracy of our methodology, we recommend ongoing acquisition of high-resolution imagery throughout the growing season to gauge what is the most effective time for monitoring. Finally, we're working on making the platform publicly available via a website that streamlines imagery upload, annotation, classification, and map generation. In addition to the funders of this project, the Coastal Zone Management Program and the National Oceanic and Atmospheric Administration, we wish to acknowledge numerous supporters in Michigan state government, Michigan conservation organizations, and within our own organizations, Michigan Aerospace Corporation and Michigan Natural Features Inventory. If you have questions and comments about our monitoring platform, we encourage you to contact us. We've provided our email addresses here. If you want more detailed information about the project, we have a technical report that's available on the Michigan Natural Features Inventory website, provided at the bottom of this slide. Thank you.